Okay, I'll continue with this figure. A word score for speech material dental as a function of speech to noise ratio SNR. And it shows when SNR in dBs are zero, almost 90% of the words are word score of 90%. If you just raise your uh, SNR by 10 dBs from, for instance, from minus 15 to minus 5 dBs, then the score will increase from 10% to or 70. So, in other words, if the background noise in a room is a problem for the understanding of speech in a room, then just a small reduction in of the background noise will be beneficial. It is time confusing and complicated to measure speech intelligibility with test subjects. Therefore, measurements and calculation methods have been developed for the estimation of the expected speech intelligibility in a room or on a transmission line. You have this articulation index. What is this? I come back to it. Determination of the signal to noise ratio in frequency bands, usually 1 octave or 1/3 octave. The SNR values are weighted according to the importance of the frequency band. The weighted values are added and the result normalized to give an index between 0 and 1. The index can then be translated to an expected intelligibility score for different speech material. Then we have the speech intelligibility index. This method is based on the AI principle, but the weighting functions are changed and a number of corrections to the AI method are implemented. One of these is a correction for the change in speech spectrum according to the vocal effort, shouting, raised voice, low voice. Then we have this speech transformation index STI. In this method, the modulation transfer function MTF from the source, the speaker, to the receiver, the listener, is determined. The MTF function is determined for octave bands of noise from 125 Hz to 8 kHz and for a number of modulation frequencies, octave bands and modulation frequencies from 0.63 Hz to 12.5 Hz. The reduction in modulation is transformed to an equivalent signal to noise ratio, yes, and is in the AI method. These values are added and normalized in order to yield an index between 0 and 1. The index can then be translated to an expected intelligibility score for different speech materials. Then we have this rapid speech transmission index. This is an abbreviated version of STI. Only the frequency bands 500 Hz and 2000 Hz and only 9 different modulation frequencies are used. The result is an index which is used in the same way as in speech transmission index. Okay, recap about simultaneous masking. We have broadband noise from when the tone frequencies are less than 500 Hz. Then the SPL is flat, about 40 dBs. When the frequency for the tone is more than 500 Hz, then there is a increase in TD per decade. That will say TdB if you go from 1000 to 10,000 Hertz, or 3 dB per octave if you go from 3 dB increase if you go from 1000 to 2000 Hertz. And then we have the narrow band masking, and we can see the excitation pattern. We have this upward spread masking. When the masking level is increased, then there's an upward spread for higher frequencies. For lower frequencies, the slope is quicker going down. But for higher frequencies, for instance, more than 100, then even if the masker frequency is, for instance, 1000 Hertz, even when the signal frequency is deviated very much from the masker frequency, you need a high signal in SPL to overcome the masking. Recap time course of masking. We remember that backward masking or pre-masking, the signal before masking, there's a gap time about 20 milliseconds. Then we have the simultaneous masking as talked about before. And then we have the forward masking when the signal is after the masker. There's a time gap of delta t about 200 milliseconds where there is an impact. Masking have an impact. Okay, remember SNR is not the only way to explain speech intelligibility. It's more than just SNR. What factors or characteristic of the channel, for instance an additive masker, could influence intelligibility? If assume that we have both noises have the same spectral energy distribution and equal RMS power. We have an amplitude and a constant noise is constant amplitude, and another one with a varying amplitude, but they have same spectral energy distribution and equal power, RMS power. Which masker is more effective and why? Yeah, listening in the dips gives masking release. That means that if the amplitude is varying in then in magnitude, then it's easier to pick up some frequencies, and then it's easier to understand. Then there will a masking release will happens. Yeah, and then this bubble noise. Yeah, I will not say much of this. It's when in the first time the consonant identification score in person is decreasing rapidly when the n is growing from 1 to maybe 8, and then it's almost constant when the number of bubblers are increasing. You can also have this information masking, IM. One definition, any masking or interference that can't be attributed to energetic masking. Okay, other way to explain it. Very broad definition, not very specific. Alternative definition, disruption of streaming or segregation of target from background. We have some room acoustics, effect or some direct sound, early reflection, later reflection, so on. Effects of reverberation on modulations. Reverberation reduces modulation depths. Gaps are filled in, so result noise has less gaps reduced listening in the gaps. That means that modulations in target speeds are reduced. You can also see on a graph if the reverberation time is increased, the speech intelligibility is decreasing. Intelligibility drops with increasing reverberation time. Reduction in modulations are detrimental to speech intelligibility. So, yeah. Speech, hearing, and speech intelligibility recap from spatial hearing lectures. We have this interoral time differences. It happens because of the distance difference, the pathway difference between the right and left ear, and we have this interoral level difference, and this happens because of the shadowing, the head shadowing of the sound waves. Okay, we can say that if wavelengths are long, then there's a lot of diffraction, and then almost if there's a direct direction to the right ear, then the heads diffract the sound waves. So almost every sound waves are registered also at the left ear, but there's a time difference because of the longer pathway. And in the ILD example, if the frequencies are high, then the wavelengths are short, then there's no diffraction. Then you catch a big level difference between right ear and left ear. Having two ears help us determine the direction of a sound source. There are two such binaural cues as from the sense of hearing. We have interaural time differences. A sound from the right arrives at the right ear first, and interaural level difference. A sound from the right ear is more intense in the right ear. Interaural time differences are dominant for most natural sounds. Interaural time differences are most useful for the location of low frequency components. Then, if the wavelength of a continuous pure tone is less than twice the distance between the ear, frequency is too high. Ambiguity arises as to whether the sound is dealing to the left or right ear. However, time differences between peaks in the slowly varying envelope can be used at these higher frequencies. Yeah. Okay, the envelopes can be used. Interaural level differences arise mainly because of the shadowing effect of the head. Low frequencies diffract more than high frequencies. So the level cue is most salient at high frequencies. Yeah. So then we have this binaural masking level difference, BMLD. If you have a right ear and a left ear, if same noise and same pure tone to both ears, tone detection is poor. But if the pure tone is inverted in one ear, tone detection is good if you change the phase. And also if the pure tone is removed from one ear, tone detection is good. A measure of the advantages in a signal detection then can result from the use of both ears. The binaural masking level difference is a difference in signal threshold between a situation in which the masker and signal have the same level and phase relation at the two ears, and a situation in which the level of phase relation between the masker and the signal differs between the two ears. So that gives us BMLD. So that was part 2. Thank you.